Okay, hi everyone, and welcome to the companion video for Data Management Week 8 and Assignment 3. Today we're talking about t-tests. It's a little bit more complicated than some of the stuff that we've been talking about previously, but what we're doing is essentially trying to start using those inferential statistics. We have some data about our samples that we get from our observations, and now we're trying to make inferences about the populations of those. And specifically, what we're trying to do in this example is compare two different populations to see if the means of our samples are the same. And what we're trying to do is get at that, are these two things statistically and significantly different? T-tests are used when we have a dependent variable. So in this case, the thing that we're interested in, that is continuous. And when we have an independent variable, the thing that we think is affecting the thing that we're interested in, that is categorical. And so in this case, we have two different samples, two different populations, and we want to know that is each of these groups of our numerical values different from one another. And so what I've done is I've created this Excel sheet here that has a brief overview of some of the stuff that we're thinking about for t-tests. Now, what you can do in this sheet is you can change these values that are in the green cells to change what the mean and the standard deviation are for our two data sets. So right now it's set that each one of our samples is a standard deviation of 25 and a mean of 50. If you type into any cell that's in this, it will update those values because they're randomly generated, or you can also press the F9 key, and that will also re-update all of these randomly generated cells. And you can see that even though we have a mean of 50 and a standard deviation of 25, you can often get really different looking box plots here, right? Some of them are thin, some of them are wide, some of them have outliers, and some of them don't. Now, if we want to start seeing what we also have in the sheet is our t-test outcomes. And so what the t-test gives you is a p-value. And as we discussed in class, the p-value is the probability that your null hypothesis is true. What this means is that you have to know what your null hypothesis is. And that in most cases when we're doing statistical tests, our null hypothesis is that nothing is happening. There's no difference between these two things. And so what this is telling us, from all of these different t-tests that it's doing, all the different kinds that we could be doing, is that the probability that there is no difference between each of these is whatever this value is. So what the one-sided equal variance t-test is telling us is that the probability that these two box plots have the same mean is 26%, 0.26. And each one of these tests is telling us the exact same thing. When we're thinking about one-sided versus two-sided, we're thinking about, are we looking in one direction, whether one is greater than the other? Or if we're thinking two sides, can it be in either direction, this difference? So with one-sided, we're saying, is the first one bigger than the other one? And with the two-sided, we're saying, is either one of them different than the other? So it's a slight difference, but you can see that it basically changes the way that we calculate the p-values. So this one is much higher. It's much more conservative in that estimate when you're thinking about, is it in either direction? Versus if you're looking at one direction, it's a little bit less conservative. So we also have three different types of t-tests that we can do. We have paired, which is when we don't have independence between our two samples. So that would assume that this ID number 1 comes from the same sampling unit. And that would be, say, are this type of leaf on this plant bigger than this type of leaf on this plant, right? Because they come from the same plant, so it's that same sampling unit. Or in the example that we're doing in class today, we could use these two ones. And what these ones do is they say, okay, we know that sample 1 and sample 2 are independent of one another. So we can just look at across all of the observations instead of trying to say, use 1 and compare those two, and then use 2 and compare those two, and then use 3 and compare those two, as in our paired t-test. So basically, paired is when you don't have independence between sample 1 and 2. And the equal/unequal variance t-tests is when you do have independence between those two. So in the example that we have in class today, all of these samples would have come from different plants that are of one species, and all of these samples would have come from different plants that are of a different species. And that's what we're looking at today. So they're independent of one another. In terms of the next thing that we need to do, we have to determine, are the variances equal or are they unequal? And so that determines which one of these types of t-tests that we use. So there's a couple of different factors that go into the t-tests. Are our observations independent between our samples? Are the variances equal? And are we looking at it one-sided or two-sided? And generally, for the purposes of our course, we're going to look at it two-sided because that's an easier way to understand these things. So what you can do with this sheet is you can actually change around the values here. So we can have standard deviation, and we can change this to being, let's say, much smaller. So now we say that the standard deviation is 10. And so you can see that as we update this, this sample 1 is consistently going to be much narrower than sample 2. We can also keep them the same, and we can change the means. So instead of this mean being 50, I'm going to change it to being 75. And now you can see that sample 1 is consistently a much higher mean than sample 2 as we change it through a lot of these times. And what happens is you can see that these t-tests, all of a sudden, they're this blue value that says that they are less than 0.05. And so it's telling us that these two samples are statistically different. And this is an inferential test. And so what we're saying is, based on these samples that we've taken, sample 1 and sample 2 of whatever it is that we're looking at, we're making an inference that these populations have different means and that they're statistically significantly different from one another. So that's what we're trying to get at here, aside from just describing what the samples are. So thinking about it has a mean of 75 and a standard deviation of 25, we're using inferential statistics to say that, to the best of our understanding, based on these samples, the populations of 1 and 2 are likely different from one another. And that's kind of what we're getting at here. Within the t-tests, I'm going to pull this over here first because this is one of the first things that we need to look at, is which type of t-test to use. And so what we want to do is test whether or not the variances are equal. And we can do this with another test that's called an f-test. And so basically the f-test checks whether or not the variances are equal so that we know which type of t-test to use to test if the means are equal. Because the means are really the thing that we're most interested in, right? We want to know, on average, does 1 differ from 2? So, with the f-test, we're testing the null hypothesis that the variances are equal. Our f-test gives us the probability that that null hypothesis is true. So, if our p-value from the f-test is less than 0.05, we can reject the null hypothesis and we say that there's a difference. If it's greater than 0.05, we can't reject the null hypothesis, and then that means that they're equal. And so I've outlined that here with colors, right? Our null hypothesis is that our variances are equal. If our p-value is higher than 0.05, that means, yes, they are equal. We have to accept that null hypothesis. If we go back over here and we change these so that the standard deviations are different between the two, let's say 10 here and maybe 50 here. Now you can see that our population 1 and our population 2 have pretty different levels with which they go away from that center. Now what we're doing is you can see that our p-value is really, really, really small. So what it's saying is there's a tiny, tiny, tiny probability that these variances are equal. So in this case, we can reject that null hypothesis, and we can say that the variances are unequal. And so the reason that we're doing this is to understand which t-test to use. So if we say that they're unequal, we use the t-test for unequal variances. And if they are equal, we use the t-test for equal variances. And it varies slightly, and it will change kind of what, how the p-values are calculated, but all in all, it's going to be a very similar method that we go about it. The other way that we're testing our assumptions for t-tests. One of the other ones is that each one of these data sets is normally distributed. When we talk about normal distribution, we talked about it a little bit in class, and what we're thinking about is the proportions of data that are certain distances away from the center. And so when we think about a normal distribution, we have this empirical rule that talks about kind of how far away from the center certain amounts of data are. So it says that 68% of data are within 1 standard deviation of the mean. 95% of all the data is within 2 standard deviations of the mean. And 99.7% of the data is within 3 standard deviations of the mean. And so that's what this kind of weird looking graph here is telling us. What we're doing is we're trying to say, does our data meet these assumptions of normality? And to do that, we could use some more complex tests, but for the sake of what we're doing here, we're just going to look at the histogram. So what we can do is all we have to do is highlight this data and then go to insert and make our histogram, and I've already done that here. So if we update this data, you can see that every time it changes kind of what the shape of this distribution of the data looks like. And what we're looking for is, does this shape kind of look like this shape? Now you'll see that in statistics, we hope that every time it looks exactly like this shape so that we can run these tests. In reality, it's much more complicated because they're not always going to be this pretty hump-shaped curve. They're going to often be kind of weird shapes where where it might be skewed to one side or the other, or it might be that you have these kind of uneven distributions of them. For our purposes, that's okay. I want you to be able to recognize when we're violating the assumption of normality, but we're not going to use a different test. And that's because those tests can get a little bit more complicated and they're really difficult to do in Excel. So for the sake of ours, I want you to know when we're violating that assumption of normality and why that is important. But we're not going to necessarily change our methods based on violating that assumption. I want you to recognize what this is, and I want you to be able to tell me why it is important. And the reason that is important is because our test assumes that all of the data is like this. And so when it's comparing those two means, like we looked at in class, it's comparing those two things and saying, well, what's the probability that these means are actually the same? And if the data doesn't look like this shape, then our test is going to do something that we might not have as much trust in. So when it comes to these assumptions, we're looking for close, but we accept that we have some variation, and we want to understand, well, how is the data set that we're using potentially going to affect the results of this model, this test that we're using, and how that affects what our conclusions can be based on it. So this is a sheet that's available to you in the week 8 content. I want you to play around with it a little bit, test some of these standard deviations and means, and try and understand how the standard deviation affects how far away the data are from the mean, how kind of wide that box plot looks, and how we can understand when populations have close means, if we can tell that they are statistically different from one another, or if they are not able to be determined to be statistically different from one another. So I want you to pause this video now, play around with this for a little bit, try and see if you can understand when it's saying that they're different, when it's saying that they're the same, based on changing between the standard deviation and mean values. Okay, welcome back. So now what we're going to do is we're going to go into the assignment 3, and we're going to start calculating our t-tests for different independent variables. And so in this example that we're using for assignment 3, I got this raw data from an example data set that's present in R statistical analysis, which is a programming language that you can use to do a bunch of really cool stat stuff. If you're interested in that, come talk to me and we can chat about it. We're not going to get into it in this class because it's a little bit above and beyond, but it is a really cool tool that I can talk for hours about. Now, this is what that raw data set looks like. So you can see we have a species, and we have 2 of them. So we have species setosa, which is Iris setosa, and we have species Iris virginica. And then we have different measures in this kind of wider data set of independent variables, which is the petal width, the petal length, the sepal width, and the sepal length. And what these are, they're parts of the flower. So we have our standard petals, and then we have this kind of modified sepal, which is where the bee lands. And we have lengths that they've measured for 50 different plants, 50 different flowers of Setosa, and 50 different flowers of Virginica. What I've done to make your assignment easier for you is move these onto a sheet in the format that we need to do our t-tests. And so you see that you have one sheet for sepal length, one for width, one for petal length, and one for petal width. In addition, I've created this summary table where you're going to put your results so that you can put it directly into your reports. So what we're going to do here is we're going to work through one of these independent variables together, and then you're going to be able to do it on your own with the other three. And for the bonus, you just have to calculate the sepal area, which is length times width, and the petal area, which is length times width, and do the same thing for both of those. Now, we go to sepal length, and you can see that we have these two data sets. So the first thing that we're going to do is format it as a table. So we press Control L, and you can see that it, because I'm on this one, it recognizes that, and we can create a table there. If you are a Mac user, remember we figured this out, but what you have to do is go to here, and I believe it is Format as Table. And you can pick one of these lovely colors, and it will format it that way. And you can do the same thing. Now, we have this table, and under Table Design here, you can see that, in this, so we can see it, it has a name. This is Table 4, but I want to call it sepal.length. And that's so that when we're referencing things later, we can tell that it's referencing from this table. So, the first thing that we're going to do is test our assumptions of normality. What we want to do then is we highlight all of Setosa. So I can highlight this top cell here. I can press Control Shift down and highlight the whole thing. Then I can go to Insert, and I can make a histogram. That's a pretty good looking histogram. So what we can tell here is, because this is put down here, I can Control X to cut it, and I can paste it up here just so that it's moved. And we'll call this one Setosa. Now, this looks a lot like our normal distribution, right? This hump-shaped curve here. And that's all that we're looking for here. So I can see that Setosa, based on this, is approximately normally distributed. That's one of my conclusions right there. We're talking about how this data set is distributed, and just because it's kind of this hump-shaped curve, this looks pretty good for the purposes of what our t-test is going to do. Next, what we can do is we can do this again for Virginica to test that data set. So we copy this one, we can paste it just below, so Control C to copy, Control V to paste, and now you see that it's the exact same graph. But if we go and we highlight along the edge of the data that it's talking about, we can actually drag it over by finding this little crosshair, and we can move it just right over to Virginica. Now we can change this name, Virginica, and we can look at this one and we can say, oh, that looks pretty good too. So I would say that Virginica is also approximately normally distributed. Now we know that we have met our assumptions for normality. What we're going to do next is test our assumptions of equivariance. And we do that with the f-test to figure out if we use the t-test with equal or unequal variances. Now there are two different ways that you can do this. The easiest one is to use the f.test function. So I'm just going to write this out, f-test using Excel functions, and what we're going to get is a p-value. So in this cell, we're going to write equals f.test. Oops, why did it do that? F.test, and you can see that once we're writing in this formula bar, it says, okay, you want to do an F-test, which means that you're comparing two data sets, array 1 and array 2. So what we can do is go up to here and we can say we want to do sepal length setosa, and that's one of the reasons we have it formatted as a table, so that you can see that it's just taking that whole column of sepal length setosa, and we want to compare that with the variance of sepal length virginica. Now, for the F-test, that's all we need. We click enter. So this is a very, very small value. It's saying it's 6.3 times 10 to the power of -5. Now, you should know a little bit about the scientific notation from your math classes, but what that means is essentially that we have a number here that is really, really, really small. And so it's saying that it's 0.000064. So what that means is that I'm going to write this just in the same column here, our p-value for the F-test is less than 0.05, which means we reject the null hypothesis that variances are equal. This means that we use the t-test assuming unequal variances. And so this is the probability that our null hypothesis is true. This is saying that the probability that these two variances are the same is really, 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 really small, which means that they're very likely to be different. And again, this kind of gets into the philosophy of all this stuff that says that we can never really know, but we have a lot of evidence based on these two things that supports that these two things are different. So that means that we use the F-test for unequal variances. So that's the easiest way to do it. The other way that we can do it, which gives us a little bit more information that we don't necessarily need, but is also good to understand how we can do it, is to use the data analysis toolpack. If you don't have data analysis in your data tab up here, what you need to do is go to File, go to Options, and go to Add-ins. You can tick this Excel add-ins, go, and make sure that this analysis toolpack box is ticked. This is also available in the assignment instructions so that you can get to that. Once you have that box ticked, you can click this data analysis tools. And what that does is it allows us to do all of these different things. And so we can get a whole bunch of different information about this from our data analysis toolpack. So we can do this F-test to sample for variances. And we can click OK. What this does is it says which variables do you want to compare. So in this case, my first variable that we want is going to be setosa. So I highlight all of those using Control-Shift-Down. And our second variable is going to be virginica. So I highlight the first one, and then I do Control-Shift-Down to highlight the whole thing. It says, where do you want to output this? And so we can highlight this, and we can pick this cell to output it. And it tells us what's our alpha. And this is that level of significance, that level of confidence that we want to have in where we're saying the null hypothesis is cut off. So this is saying that we want to have 5% certainty, and we're using that as we want to have 95% certainty, sorry. And so we're using this 5% cutoff. So we click OK, and you see that we have this pop up here. Now, this is calculating a two-sample p-value, and you'll see that it's a little bit different than here. But what this one is doing is, I believe, a two-sided F-test, whereas this one is doing a one-sided F-test. And so you're going to get different values, but generally they'll give you the same result. And so here we can see that our mean of virginica, or of setosa, is 5. Our mean of virginica is 6.5, and that these are the variances that we have for both of those measures. And they have 50 observations each, and the degrees of freedom, which is the statistical jargon for how many samples we have, is usually the number of observations minus 1. and so we have a 49 degrees of freedom. It calculates this F statistic, which is based on the ratio of the variances to one another, which you don't really need to know for the purposes of this, as much as this value here, the probability that F is less than F. And so this is our p-value here. And so what this is telling us again is that this is 3.18 times 10 to the negative 5, which if we format it as a number, again, we can see is a very, very, very small number. About half of the one that we're looking at for the two-sided t-test, or two-sided f-test. And so in this case too, what we can say is that the p-value for the f-test is less than 0.05, which means that we reject the hypothesis that the null hypothesis is true, and we use a t-test assuming unequal variances. So that's us checking our assumptions so far. Now we know that we need to use a t-test assuming unequal variances. So what we do is we can use our Excel function. And so again, we're going to get a p-value, and we do equals t dot test. And this returns the probability associated with a student's t-test. So we have a couple more things that we need to add into here. We have array 1, array 2, we have our tails, and our type. So for array 1, we're going to pick Setosa again. For array 2, we're going to pick Virginica, because these are the two data sets that we want to compare. We're going to say that we want to use 2 tails, so we click 2. And we're going to say that we want this, and then this final type option is which type of t-test do you want to use? And so we want to use, do we want to use paired? No, because they are independent of one another between those two data sets. Do we want to use 2-sample assuming equal variance? No, because we just did our f-test that says that these variances are unequal. So we typed 3, saying that we want to use the 2-sample unequal variance. We close our bracket and we press that. Now, what this is telling us is that this is an incredibly small number. So 3.97 times 10 to the 25. So that is very, 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 very small. So this is an infinitesimally small probability, according to these statistics, that these two means are equal. What this means, I'm going to put this back to scientific just so that we can see it. Where is it? There. Is that the p-value for the t-test is much less than 0.05, which means we reject the null hypothesis that the means are equal. The mean sepal length is statistically and significantly different between species. That is our conclusion. Now, we can also use this during the using the data analysis tool pack. So we can go over to data analysis, and we go boop, boop, boop down here. And you see that we have 3 t-test options. Do we want to do paired? No, they're independent of one another. Do we want to do equal variances? No, we know that the variances are unequal, so we pick the unequal variances. Now we do the same thing where we pick our range for Setosa, we pick our range for Virginica, our hypothesized mean difference. What do we think that the difference is? Well, our hypothesis, our null hypothesis, is that there's no difference, so we put 0 here. Then we say, where do we want to put the output? We click in there, and we can pick here. Now we output that. So this is doing the exact same thing, and it's telling us that we have a slightly different number, but almost the same kind of level of certainty, that the p-value for our two-tail distribution is much less than 0.05, which assumes that, which means that we can reject our null hypothesis that they're equal, and we can say that these means are statistically different from one another. So that's essentially what we're trying to get at here. But there's a couple of other things that I want you to be able to put together. So one of them is a box plot. So let's just look at these, right? And see if we can understand it. So we highlight that whole table there, which you can use with the Control Shift, or you can highlight anywhere in it and press Control A. And then we're going to go to Insert. Actually, we're going to press Control A twice so that we get those headers there. We're going to go to Insert. We're going to go to, where is it? These statistics charts, and we're going to make our box and whisker. So now we can see that we have this graph. And based on our tests, we know that there's a lot of, we know that this is a statistically significant difference. So in our figure captions, we can write that. Now, what we want to do is make this chart great. So we're going to take away that chart title, add our axis titles, we're going to add a legend, and we're going to make sure that we tell everyone that these are our species. We can get rid of this label of 1. We can say that this is sepal length, and it's in millimeters. All of the measures are in millimeters. Could you imagine? Oh, yes, I believe they're, or actually, I believe they're in centimeters. That's my bad. Because irises are pretty big flowers. So they're in centimeters. Now we have this lovely graph. We can also get rid of these grid lines if you want. Don't need them there. And this is starting to look like something that we could put right into a report, and we could start to tell people. And in our figure caption, we would say something along the lines of figure X. I'm going to actually just move all of this down so that it's below here. So we would say something like figure X, sepal length with our unit for 50 observations of Iris setosa and 50 observations of Iris virginica. There is statistically, oops, not statistically, significant difference in the mean sepal length between species, p-value for two-sided t-test assuming unequal variances equals and we have this value here, 3.37 times 10 to the negative 25. And so this is a lot of information that we're putting here, right? So we have our species, we have the number of observations of each of them, and we have the results of our inferential statistics test, our t-test, so that we can put all of that together and understand that when we put that into a report, this gives us a ton of information about what we've done and what our conclusions were. There's one other tool that I want you to use before we go ahead and put our results into the summary table. So we're going to go down here and we're going to use one last data analysis output, which is our descriptive statistics. And so what we have done in the first class was calculate all of these different statistics based on using the Excel formulas. What this tool allows you to do is if we highlight our whole table, so both of these columns, including the headers, we tell it that yes, there's labels in the first row, which is the species names, and then we can tell it where we want it to output these results. So we click in there and we say, I want you to put this right at the bottom here. And we can pick what things that we want. So summary statistics, confidence level for the mean, and then the largest and the smallest. But we're just going to pick the summary statistics. And we make sure that it knows that it's grouped by columns, not by rows, and we press OK. So now you see that we have this table that gives us a bunch of really cool stuff. So it gives us our regular things that we're more familiar with, which is our mean, standard error, median, mode, standard deviation, sample variation, range, minimum, maximum for each of these different populations, the sum, the count. So our n is 50, the total sum of the lengths, which doesn't really mean anything, our maximum, our minimum, our range. It gives us all of these wonderful things. It also gives us these measures of kurtosis and skewness. And so skewness is kind of thinking about that distribution on whether it goes to one of the sides or the other. And the kurtosis is also thinking about the shape of it in terms of how closely it fits to the normal. So we'll do more on using these to kind of understand normality later. But again, for the sake of this assignment, what we're going to do is just look at the shape of these curves to determine if it fits those assumptions of normality. So now, what we're going to do is move all of our results from sepal length over to our summary table. So for our F-test outcome, variances were significantly different. We had to use the unequal variances test. Our T-test outcome, the means were significantly different. And the assumption of normality was that both species were approximately normally distributed. That's it. This is the table that's going to go into your report where you're going to put all of your final results. And I went through the luxury of actually even creating these drop downs for you to just enter what it is that we need there. You'll give this an appropriate table caption and you'll be able to throw that into your report. So what you're going to do is all of this. You can make it look nice so you don't have to do it in this order. I don't care how it looks as long as you have these things for sepal width, petal length, and petal width. If you want the bonus marks, you're going to calculate how, the petal area, which would be this times this, and you're going to calculate the sepal area, which would be this times this, and you're going to do the exact same thing another 2 times. And you can add that in just below. So if you did your sepal area, you'll see that because it's a table, it recognizes that you just entered a new line and you can just do these things with it. I'm not going to show you exactly how to do that. I think you can figure it out. So that's our video for today. If you have any other questions, please feel free to email me and we can set up some time to chat about things.